Welcome back. I'm Dr. Ajay Kumar, and I'm going to take you through a few more conceptual things in research methods. And in this particular presentation, we are going to deal with four issues. One is on study design, the second one is on study population, something about sampling, and something on variables. Now, by this time, it must have become very clear that as you begin to write your protocol and your method section, these are some of the subheadings that go into the method section. And we need to be very, very clear about each one of these issues as we begin to develop our protocol. Let's go through one by one. Let's kick off with study design. Now, it's important that any research that we do and write up, we must be very, very clear as to what the design of the study is. Because based on the design, we know what are some strengths, some limitations, how far we can go in interpretation. All of that will depend on what's the study design. And we need to know what are the kinds of study designs. So let's go through this particular classification. This is given by David Grimes and Kenneth Schultz et al. It was a publication in Lancet. The paper should be there in one of the resource materials to you. And let's go through. This slide is one of the take-home slides of this particular presentation. So let's kick off. The first question you ask whenever you look at a study is, did the investigator assign exposures? If the answer to this particular question is yes, then this is an experimental study design. If the answer is no, it's an observational study design. This is the main classification: observational studies and experimental studies. And let me take an example and sort of use the same example in different situations. Let's take an example of smoking and lung cancer. So how do you design an experimental design if you want to study smoking and lung cancer? You take a group of people who are all non-smokers to begin with, and then randomly allocate a part of this to smoke and the part not to smoke. So then the investigator is actually assigning who has to smoke and who doesn't smoke, who doesn't have to smoke. So this is a case of assigning exposures. That becomes an experimental design. Whereas in an observational study, the investigator doesn't assign exposures. Some people choose to smoke, some people don't. And as a researcher, you simply observe what happens to this group who started smoking and what happens to this group who did not smoke, and see what is the outcome, in this case, lung cancer. So that is the main distinction, and each one of you should be able to very clearly differentiate this. And under observational study, the next question you ask is there a comparison group explicitly in the design? And if the answer is no, then it becomes a descriptive study. If the answer is yes, then it becomes an analytical study. So for example, under descriptive study, the two important kinds of study designs is, one is case report, the other one is case series. We'll go in a short while in greater detail as to what are these. Under analytical study design, where there is an explicit comparison group, depending on the direction of our study, we classify into three further categories: the cohort study, the case control study, and the cross-sectional study. In a cross-sectional study, the exposure and outcome measurement happen at the same point in time. Whereas in a cohort study, you begin from the exposure and go towards the outcome. Whereas in a case control study, it's just the opposite. You begin from the outcome and see what is the prevalence of exposure in cases and controls. So depending on the directionality of exposure and outcome analysis, we have three designs: cohort study, case control, and cross-sectional study. Now, cross-sectional study sometimes is also known as prevalence study and is used to understand prevalence of various diseases or health-related events, in which case it is also classified as descriptive study. by some people, which is fair enough. If you are using it just to measure the burden of certain things and just report that, then it is a descriptive study. Whereas if you use it to look for associations, which and make internal comparisons, then probably there is an analytical component as well. So cross-sectional study can be put either as a descriptive study or an analytical study. Now, under experimental study, you can again divide, which is not shown here, with controlled group or without control group. So for example, the phase 1 and phase 2 trials do not have any comparison group. The idea is to study pharmacokinetics, safety, and preliminary efficacy details. So where there is no explicit control group. But if you have a control group, then they're further divided into whether it is a randomized control trial or a non-randomized control trial. So essentially differentiated by how the participants are allocated to the intervention group, whether it happens based on random number tables, happens by a result of chance, or by some other pattern. So depending on that, we have two designs here, randomized control trial or non-randomized control trial. This is essentially trying to classify all possible study designs. Now there are a couple of study designs when populations are units of observation instead of individuals, and I'll come to that with greater detail a little later. But there are two important study designs. One is called ecologic studies. The other one is called community-based trials. So ecologic studies are studies of aggregate measures of populations, and this is one of the observational study design. Whereas community-based trials or field-based trials are basically experimental designs, but which happen at the level of community. And we'll take a few examples to know these things in greater detail. So one of the things to clarify right up front in terms of directionality of exposure and outcome measurements, especially because there is often a lot of confusion. In a cross-sectional study, you're measuring both exposure and outcome at the same point in time. When I say at the same point in time, this is with respect to the study participants' time. Quite often I find people do a cohort study but describe it as a cross-sectional study, and let me briefly explain here. So one of the commonest designs in the TB world, especially in operational research, is to review the records and find out several questions about what are the outcomes among TB patients, is it related to HIV, etc., etc. But people describe this is actually a cohort design because you're taking two groups, one who are co-infected with HIV, one group which do not have HIV, and then look at treatment outcomes, which could be death, default, treatment success, etc., etc. It's actually a cohort design. Even though you are using retrospective data from the databases or TB registers, the directionality is from exposure to outcome, and so it becomes a cohort design. But many people describe this as a cross-sectional because from the investigator's perspective, it is cross-sectional. The investigator measures both exposure and outcome, both extracts information on exposure and outcome at the same point in time. He just goes to the database, gets both at the same point in time. But from the patient's perspective, it is not at the same point in time. Clearly there was a time when they tested for HIV, which is at the beginning of TB treatment, and then there was a follow-up of 6 to 9 months, and then the outcome develops when you document whether death or treatment success, default accordingly. So it is actually a cohort study. This point needs to be very, very clear. And some people also use this cross-sectional to think in terms of calendar time, which is not correct. So for example, if it's a nationwide TB prevalence study, it may take a long time. It can't be done at the same calendar point in time. Depending on the scale of the study, it may take several months to contact all study participants. But whenever a participant is met, we measure both exposure and outcome at that single point in time. So just because it takes several months for data collection, it doesn't become a prospective study or a cohort study. It is still a cross-sectional study. So this point needs to be very, very clear. Now let's go through individual study designs and see how each one of them differ. So let's look at what's a case report. A case report is one of the commonest form of publications. It's basically a report of a medical oddity. Something unusual has happened and we would like to report that. Maybe it's a common presentation of a very uncommon disease or a very uncommon presentation of a common disease. Somebody said that if you can make one big talk, then even one case report is important. Exceptions to the general rule, even if it is one, is important. And this is the topic that gets in case reports. For example, all our knowledge about which part of the brain is involved in which function actually comes from studies and several case reports among brain injured patients. Some accident happens and then some part of the brain gets injured and people lose some function. So it is studying such people, we are now able to map out what are the normal functions of the brain. And such things are usually the topic in case report. The second descriptive case study design is a case series, very popular among clinicians. It is nothing but description of a series of cases of interest. And both case report as well as case series are often very useful to generate hypotheses about possible associations. For example, our initial, today we know very well that smoking causes lung cancer. But at one point in time, it all began as a case series. There was a surgeon somewhere in the US who saw that all the patients he was operating, all the lung cancer patients he was operating on were heavy smokers. So that was actually led him to think that there is something associated with smoking and lung cancer. And that in fact in turn led to several other studies, case control studies, cohort studies, before now we accept that smoking in fact causes lung cancer. But it all began from a case series. Similarly, the other case series, the example I showed, the 12 cases of totally drug-resistant tuberculosis from India. That is another example of case series. Here was a TB case which is resistant to all the drugs that we have. So this was dramatic. And then, he had 12 such cases. So it's very, very interesting. And it led to several hypotheses as to why this is the case and what we should be doing about it. And in fact, we can give several examples. It all began from a case series. Let's move on. What is a cohort study? As I told you, in a cohort study, it is again an observational study. You begin from exposure and move towards outcome. So you begin from a group of people who are exposed to something, not exposed to that thing, and then follow them up over time. And then see whether they develop outcome or not. So if you go with the same example of smoking and lung cancer, you put together a cohort of people, some smoke, some don't, and then follow them up. At the point of putting together the cohort, none of them have developed outcome. That is one of the important criteria. They are outcome free. And then you follow up over time to see how many of the smokers develop lung cancer, and the same thing you do with non-smokers. And then you can see, is smoking associated with lung cancer? So one of the advantages of a cohort design is that you can study multiple outcomes of a single exposure. So as you put together a cohort of smokers and non-smokers, you can study lung cancer, but you can also study coronary artery disease, or you can also study is smoking associated with esophageal cancer, for example. any number of outcomes can be studied in a cohort design. So this is further taking. So for example, if you look at exposed and then see what is the incidence of disease among exposed, what proportion of exposed develop disease, and you do the same thing among the non-exposed. And if you find that the incidence of disease among exposed is higher as compared to the incidence of disease among non-exposed, then you can see very well that probably this particular exposure is associated with a higher risk of developing disease. Well, do you always begin a cohort study from exposed and non-exposed? Well, not necessarily, and I'll give you some examples. Maybe you've heard of this large study called Framingham Heart Study. And Framingham, in this case, is actually the name of a place. And all the people staying in Framingham were enrolled into the study. So you are actually putting together a cohort based on some other criteria like a defined population instead of an exposure. And the reason why you do this helps us to study multiple outcomes of multiple exposures, because once you define your population, you can also measure several exposures of interest at that point in time. And so you are developing several internal cohorts and then follow up to study several outcomes. So it is possible to put together a cohort based on some other criteria other than exposure, in which case it helps you understand multiple outcomes of multiple exposures. So one of the common study designs in the TB world is a cohort study of TB patients who are registered in a particular area in a particular year. And then you can study, is HIV related to treatment outcomes, or you can also study, is diabetes related to treatment outcomes. So you can study multiple outcomes of multiple exposures in a cohort study. Just need to carefully think this through and put together the cohort. Now, is a cohort study always prospective? Not necessarily, and it's well illustrated in this diagram here. So if you begin your study today, if you put together your cohort today and follow up prospectively in future, then it becomes a prospective cohort study or a concurrent cohort study. But you can also do a similar thing going from exposure to outcome by looking at databases or retrospective charts, patient registers, in which case both exposure and outcome have already occurred, but your direction of study is still from exposure to outcome, and that is called as a retrospective or a non-concurrent cohort study, in which case both exposure and outcome have both occurred. And then there is another design which is a mix of both. So there is a component of retrospective cohort study. So you begin with an exposure that happened, let's say 2 years ago, and look at the outcomes today, and then follow it up for future. So you have a component of prospective as well as a retrospective. Such designs are called as ambidirectional cohort studies or ambispective cohort studies. Please note that the term that we are using, prospective or retrospective, refer to the calendar time point here. Well, what are the advantages of cohort study? I think it's very intuitive and easy to understand. It begins from the exposure and moves towards outcome. The biggest advantage of a cohort study is that you can calculate actual incidence of outcome, actual risk of outcome. As a result of it, you can directly get relative risk or risk ratio. And hence, we can also calculate possible attributable risk and population attributable risk. We'll learn more about these terms in other presentations. But suffice it to know that this is one of the biggest advantages of a cohort study. You get the estimate of relative risk directly. And it is very, very well suited for rare exposures. For example, if you want to know what is the risk of cancer among people working in uranium mines, who knows, how many of you know who is working in a uranium mine. It's pretty rare exposure. So in which case you can go to a place where there are people working in uranium mines and then put together a cohort, follow them up to find out what is the risk of cancer. So whenever an exposure is rare, cohort study is ideally designed for that. And it's also a very useful design when the duration of follow-up is small. If there is a long duration, then the problem of cohort studies is that many people are lost to follow-up, and then there are compromises to the internal validity of the study. But if the follow-up duration is small, then this is a very useful cohort design, useful study design. And I'll give you two examples here. For example, all the studies of pregnancy and outcomes, it's a great place to do cohort study, because we know for sure that it's about 9 months. Pregnancy is about 9 months. So we will finish the study in 9 months. So that's another one example. The other example is in the TB world, for example. You can look at outcomes among TB patients and look at several factors which are associated with treatment outcomes. Again, we know for sure that a TB patient completes his treatment in a matter of 6 to 9 months. So again, very useful design is a cohort study. But as some of you might now be guessing, what are the disadvantages of a cohort study? I think one of the disadvantages is outcome ascertainment bias, especially if the investigator knows what is the exposure and knows what is the hypothesis under study. And the other, there could be other biases due to the quality of information obtained may be different for exposed and non-exposed, or due to non-response and losses to follow-up. Loss to follow-up is one of the biggest problems with any cohort design. So especially if there is a long follow-up to be done, 10 years, 15 years, there will be a lot of people who are lost to follow-up along the way, and that causes severe problems in internal validity. So clearly, if there are long follow-up periods required, or if there are rare outcomes to be studied, which means that you have to put together a large cohort to even see a few outcomes, then probably cohort study is not the best design. You must choose another alternative. And often we find in cohort studies large sample sizes and pretty expensive, resource intensive. And quite often we also see that there are some ethical issues, especially in prospective cohorts. Quite often we find that we begin with the cohort study, and a year down the line we have information coming from other studies which clearly indicate probably this exposure is a risk factor. And then there are ethical issues. Do you continue with the cohort? Do you inform people about the risks of this exposure? What do you do? So there are also ethical issues in studying. So these are some of the disadvantages of cohort study, and many of which can be overcome by another study design called as case control study. Please note this. I see several people using case control for all kinds of studies. And any study with a comparison group, they consider it as a case control study, which is not the correct way of looking at it. What is a case control study? What is a case and what is a control? A case is somebody who has developed the outcome, and a control is somebody who has not developed the outcome. That is how you differentiate a case and a control. It depends on the outcome that is under study. And in a case control study, you put together a cohort of cases and controls, that is people with the outcome and people without the outcome, and then ask them whether they were exposed to a particular thing. So by design, you can study multiple exposures of a single outcome. And it's a very useful design, especially if you are trying to learn and explore of a new disease. For example, you don't know what are the possible exposures. So you can go on a fishing expedition here and study as many exposures as you want. Put together a case control study and learn about as many exposures as you want. So this is one of the great design when you want to do an exploration. It's relatively rapid because the outcomes have happened and the sample sizes are usually very small, and so it can be done at lesser cost. It's efficient, so cost effective study, especially when the outcomes are rare. You want to go for a case control study, because if the outcomes are rare, if you want to do an incident study or a cohort study, it's going to take a long time and requires large number of people in the study design and makes it very, very expensive. Whereas in a case control study, you can directly pick people with the outcome, have a comparison group without the outcome, and study what is the prevalence of exposure in both. And it is also suited for diseases that take a long time, just like cohort design. Wherever cohort design are not suitable, case control study helps. So let's recapitulate what are some of the disadvantages of a case control study. One, you can study only one outcome in a case control study. Two, it's not suited for rare exposures. We have already talked about it. In rare outcomes, case control study, whereas in rare exposures, the preferred design is a cohort study. Number three, you can get only odds ratio as a measure of effect in a case control study. So you cannot get a direct relative risk, because measurement of incidence or risk is not possible in a case control study. So you get an odds ratio, and in instances of rare outcomes, odds ratio is a good approximation of relative risk. But the most important thing we have to worry about in case control study are the biases, and that is what has given case control study its bad name. And there are two important biases. One is selection of the controls, and this is the hardest part. And many people even go on to say that, give me your hypothesis, then I'll accordingly tell you what controls you have to choose to ensure that your hypothesis is correct. So this is something that we have to worry all the time, and to ensure that controls actually represent people without the disease, or the population, or the study base, which is nothing but the population that gave rise to cases. So are our sampled controls representative of the study base? That's going to be the crucial question, and we'll have to think it through at the design stage to ensure that we have got it right. The other bias is information bias, and there are different kinds of information biases. One of the common ones is a recall bias, because we are relying for exposure measurement on the recall of the cases and controls. So the ability of cases and controls to recall certain exposures may be very, very different. For example, let's take an example of, let's say we want to look at, is maternal flu during pregnancy related to delivering a congenitally malformed baby? Now, if you look at a lady, a mother who has delivered a congenitally malformed baby, she is, devastated, and she has already gone through a great process of introspection. She might have lived her pregnancy several times over, thinking, what wrong have I done? Is it that drug that I took? Is it the smoking? Is it the infection that I got? Is it this? So she knows exactly what has happened in her pregnancy. Whereas another woman, a woman who has happily delivered a normal baby, is just happy about it, and probably even forgotten what has happened. And so she has not gone through the same process of introspection as the cases. So the ability of the cases in this case to recall something that happened during pregnancy is much better as compared to the ability of the controls, and that can lead to certain biases. This is called as recall bias. So these are some of the disadvantages of case control studies. So we have to be careful when we are choosing our study design. The other study design which I spoke about is a cross-sectional study, and as I told you, in a cross-sectional, it's like taking a slice at a point in time. At that point in time, you measure both exposure and outcome. Let's take an example. Let's say I want to study, is obesity or being overweight associated with osteoarthritis of knee joints. Now, I can just go to the people, measure whether they are, obese or not, and also measure by some means whether they have osteoarthritis or not at the same point in time. And then we can, let's say, we find that people who are obese are at a higher risk of having osteoarthritis as compared to those who have normal weight. But what is the problem in this design? The basic problem with this design is that we don't know which caused what, which came first. Did exposure come first and then the outcome, or the other way? The temporality of association we cannot dissect in a cross-sectional study. For example, in this instance, we can conceive that it could have happened either way. People first become obese. As a result, there is a lot of stress over knee joints. As a result, they develop osteoarthritis of the knee joint. But it could also happen the other way. It can be conceived that people first develop osteoarthritis of knee joint. As a result, they cannot move. They are not able to exercise. They are not able to jog. They are not able to walk. And they eat a lot but can't exercise, and then become overweight, become obese. So this is one of the crucial issues in a cross-sectional study. And the second thing in a cross-sectional study, second limitation, is that you are always studying prevalent cases. It is a survey of survivors. So if there are people who have developed the disease and have died, they are not there in your cross-sectional study. The cross-sectional study essentially captures who are alive. And so whatever factors that we find as associated with the outcome is not just the risk of that outcome, but also risk and survival with that particular outcome. But there are several advantages as well. One is it's very useful to determine prevalence or burden of several problems. Disease burden, knowledge, attitudes, behaviors, and these are very, very helpful in planning of services. For example, if you want to design a national program for a particular country, we want to know essentially how many cases do we expect in a year. And that kind of information you'll get in cross-sectional study. How many numbers of TB cases are there in a country? And then you can plan accordingly how many staff you require, how many drugs you require, etc., etc. And it's usually relatively rapid and inexpensive because it's one point in time, there are no follow-ups, and it does indicate possible associations, although you will not get it fully teased out in the first pass, but it provides indicators. Maybe this is something that we need to study further. I think I've already said about the disadvantages. The main disadvantage is the temporality of association is not at all clear in a cross-sectional study. And the associations, even if we find out in a cross-sectional study, it reflects not only risk of outcome, but also chance of survival after the outcome has developed. So these are the two important disadvantages. So this is a short overview of observational study designs. Let's go to experimental study designs. As I told you, even in experimental study designs, you can have with comparison group, without comparison group. And the example that I gave earlier, without comparison group, are the phase 1 and the phase 2 trials. Phase 1 trials are essentially among normal volunteers when the purpose is to assess pharmacokinetics and safety of the drug that is being administered. In phase 2 trials, instead of normal volunteers, you take patients for whom this drug is designed, and then again you are looking for safety data, pharmacokinetics, and efficacy data. So these are examples where you have experimental designs, but there are no explicit comparison groups. Whereas with comparison group, it's usually the phase 3 trials, and there you divide where it's randomized control trials and non-randomized control trials. So this is very well reflected in this particular diagram. You begin with the study population, take a group of people on whom you want to study a particular treatment, then you randomly allocate people to one treatment vis-a-vis the other treatment, and then you follow them up to find out how many improve when they are put on each treatment. So this is a classic design of randomized controlled trial. There are some other experimental designs which are rare, but they do happen, like crossover trials, factorial designs, etc., etc. But those are usually, rare and beyond the scope of current presentation to discuss. Let's look at a couple of other study designs. One is ecologic studies. Now, I have to clarify that this is not study of ecosystems. Ecologic studies here mean they are correlational studies and using aggregate measures of the populations. And as I told you earlier, the unit of observation here is a population rather than individuals. And I'll give you some examples. For example, the example I gave you in an earlier presentation, the association between fluoride content of public water supply and the rate of dental caries. Now here we are not talking to each individual whether he drinks water which has fluoride content and then dental caries. Here we are looking at communities. We have information on fluoride content of public water supply in a community and also information on dental caries rates. And we just take those two, do a scatter plot and see is there an association. So these studies, ecologic studies, are very quick to conduct, often uses existing data and doesn't require any ethics approval, no interaction with patients, nothing. We are usually using existing data sets and get information, do a scatter plot, see if there are associations. And often this can be the first step to identify possible hypotheses and possible associations which can be studied in greater detail using other study designs. Let's take another example. Now this shows a correlation between dietary fat intake and breast cancer by country. So for example, and what does it show? It shows that higher the average dietary fat consumption for a country, higher is the breast cancer incidence for that country. So, all we are doing is getting aggregate data for each country. One is rate of breast cancer or incidence of breast cancer. This is usually published in some global reports. And also get information on what is the average dietary fat intake and then draw a scatter plot. And you can see that there seems to be some correlation here. And one of the temptations that we have when we look at a graph like this is to conclude that dietary fat is the causal factor for breast cancer. And there is a problem in drawing such a conclusion. What is that problem? The problem is we are using aggregate data to make individual level inferences, and that is not correct. For example, given the same situation, we can even think that a person with breast cancer was actually consuming less fat. It is the other people who were consuming more fat, and so the average fat intake is much higher. So this problem of taking population level data and making individual level inferences is what we call as ecologic fallacy. And we can look at several examples with this particular thing. Now, this is very nice design. Ecologic studies can be done very quickly and can get to possible hypothesis about associations, but we cannot really say A caused B. Correlation is not equivalent to causation, and that must be remembered. So let's move on. Are ecologic studies that bad? Not so much. It can be done easily, and if we are careful with our interpretations, it is very, very useful. Sometimes some of the exposures are not individual level exposures. They are group level exposures. For example, availability of foods in the local market and its association with pellagra. This is a classic study by Goldberger et al. Where they studied food availability in the local markets, and they found that was strongly associated with the occurrence of a vitamin deficiency disease called as pellagra. And this could only be studied using an ecologic design. Or let's say if you want to study, is there an effect of anti-tobacco legislation on tobacco use by individuals? So let's say you take countries all across the world, ask one question: do you have a law for tobacco use in place or not? And then you look at the tobacco use prevalence in each of these countries. Draw a scatter plot and see, is there a correlation between the two? This is an example of ecologic study design. And, and in some cases, ecologic study designs may be even better than individual study designs, individual based study designs. For example, if within population variability of the exposure of interest is low and between population variability is high, then probably ecologic study designs are more useful. Let's say you want to examine the relationship between salt intake and hypertension. And let's say we assume that everybody in a community consumes large quantities of salt, probably greater than the threshold for developing hypertension. Then if you do a study in that particular community, an association between salt intake and hypertension may not even be apparent in studies of individuals, because everybody is taking large quantities of salt. But if you want to design an ecologic study design, then you can take communities, and then each community you take an average salt intake, hypertension incidence, and then make a correlation if salt intake is in fact related to hypertension. So it is a useful design. A sort of counterpart in experimental studies for ecologic is a community-based trial. Remember the example of fluoridation and dental caries? So this is a community-based trial that happened in New York, where they actually took two communities, Kingston and Newburgh, with similar rate of dental caries to begin with, and fluoridated water supplies of one community, in this case Newburgh, and did not fluoridate the water supplies of another community. And then they followed up for 10 years to find out what happens to dental caries rate. And as you can clearly see here, the community which got their water supplies fluoridated, there was a clear reduction in incidence of dental caries, making a strong case for fluoridation of water supplies. So this is an example of community-based experimental design. So to sum up and recap the study designs, the first question you ask: did investigator assign exposure? The answer is yes, it's an experiment. If the answer is no, it is an observational design. And then depending on whether you have a comparison group or not, you have within observational studies, descriptive studies, analytic studies. Under descriptive studies, the two important ones are case report and case series. And within analytic studies, depending on the directionality of our study, there can be cohort study when you start from exposure and move towards outcome, the case control study where you begin from outcome and move towards exposure, and the cross-sectional study where both exposure and outcome are studied at the same time. Similarly, in experimental designs, you have designs with control group, without control group. And within those with control group, you can have a randomized control trial and a non-randomized control trial. If the unit of observation is population instead of individuals, then you have ecologic studies and community-based trial. So this concludes our discussion on study designs, and this is one of the important things we need to put in our protocol. So I think this has to be very, very clear. Now let's move on to another important concept that we have to know, and this is on study population. And there are three important terms I want to introduce here. One is target population or reference population. The next one is accessible population. And the third one is study population or the study sample. Now, what is target population or reference population? Now this is the complete set of people with the characteristics of interest that we are looking for. This is the population to which investigator hopes to generalize the findings. For example, if you are doing a study on tuberculosis patients, is HIV associated with death among TB patients? Let's say if that is the research question, then all TB patients is our reference population anywhere in the world. That is our reference population, and that is where we want to be able to generalize. But we don't have access to all the TB patients in the world. So accessible population is a geographical or temporally available subset of the reference population. It is sort of a practical representation of the reference population. Maybe we have access to TB patients in India or in a particular province in India. So all TB patients registered under National TB Program in a district X, that is the accessible population. But we may not be even able to study all TB patients even in that particular district and want to draw a sample of that. That is going to be the study population or study sample. The subset of the accessible population which is actually enrolled in our study. And this is the group from whom we are going to collect the data and probably the group to which we can best apply our conclusions. So that is going to be the study population. So as you begin to draft your protocol, one of the subheadings would be what is your study population, and it's important to state very clearly in unambiguous terms what is the study population going to be. Which district do they belong, what time period, when they were registered, who are these people. But we must also have an idea of the population to which we need to generalize the results, and that is our reference population or target population. And this is about study population. Now we'll go on to discuss the next topic, next subtopic in this presentation, and that is about sampling and inference. What is sampling? Sampling is the act of drawing a sample from the population so that the sample is representative of population. So that is sampling. So as I told you, when studying the relationship between anything, but let's say between smoking and cancer, the researchers cannot possibly study the entire population. It's often too costly, not feasible, probably not required. If we are able to get the same information by testing a sample, why should we go and test the whole population? So we often and always, almost always sample. So we sample. So how do we sample in such a way that the results that we get out of the sample are representative, can be extrapolated to the larger population? That process is called as sampling. And what are the characteristics of sample? And one of the discussions is, the sample should be of sufficient size. And I'm not going to discuss here the rationale and how to calculate sample size. That is a topic of another presentation. But it's important that the ideal sample should be of sufficient size and quality to minimize two things. One is it should minimize sampling error. The number two is it should minimize sampling bias. Now do not worry if you do not understand these terms now. This will be discussed in another presentation. But let's say that is what we want to achieve. And now we'll look at how should we go about sampling. What is the process? The first step in sampling or drawing the sample is to define our population and determine what is the sampling frame. Now by sampling frame, I mean the list of all units in a population. That is the sampling frame. So we must have the list of all the units in a population. And once we have the sampling frame, then we have to choose a suitable sampling technique. Now we'll shortly going to discuss what are the several sampling techniques we have. As I told you, we have to determine what should be the sample size and then execute our sampling process. So let's look at what are the types of sampling that we have. Broadly, there are two kinds of sampling. One is probability sampling, non-probability sampling. Probability sampling means that each member of the population has a known non-zero probability of being selected into the sample. That is probability sampling. Whereas non-probability sampling is when members are selected from the population in some non-random, convenient or purposive manner. So non-probability sampling is not something that we do often, is something that we don't encourage. So we will not discuss too many things about non-probability sampling in this presentation. In further slides, we will discuss what are the types of probability sampling. There are 4 types of probability sampling: simple random sampling, systematic random sampling, stratified random sampling, and cluster sampling. And we are going to discuss a little more detail about each of these sampling methods. First, simple random sampling. In this particular sampling method, each element or each unit in a population has an equal probability of getting into the sample. The procedure is very simple. Take the sampling population. You need a sampling frame for sure here. You need a listing of all sampling units. Have all those units listed and randomly draw the required sample out of this. So for example, you have this population here, identified uniquely by some kind of number, and then you pick a lottery. Either take a lottery or take a lot and select your sample size. Maybe 5 is our sample size here, or you can use something called as random number tables and pick randomly. So each and every unit in this population has an equal chance of getting into the sample. That is simple random sampling. Let's look at the next one. What is systematic random sampling? This is sampling at intervals. How do we do this? So in situations, let's say, assume we have to draw a sample of 200 from a population of, let's say, 1000. How do we do that? First of all, we divide the total population by the designated sample size, and this will give us sampling interval. So in this case, 1000 divided by 200, which is equal to 5. And you choose a random starting point. Let's say a random number between 1 and 5. Let's say it comes out to be 4. You pick the 4th unit and then you select units at regular intervals. In this case, every 5th unit starting from 4. So the first unit is the 4th one, then you add 5, 9th one, add another 5, 14th one, and 19th one, and so on. So this is systematic random sampling. You have a sampling, you have the population, you don't have to list all the units in this sampling frame. For example, let's say go to a village and want to pick 100 households randomly in that village. You know there is a list of all houses, but you can begin at some point, start randomly, and then go every 5th house, every 10th house, or so on. And then you get a sample. So this is systematic random sampling. It's often very useful. The other method is stratified random sampling. One of the things is that in simple random sampling or systematic random sampling, it is quite possible that you may not get certain minority groups that maybe you are interested. So if you want to ensure that these minority subgroups are in fact represented, then you go for what is known as stratified random sampling, in which you first of all divide population into homogeneous subgroups and then take a random sample in each subgroup. Let's assume that we want to draw a sample which has a representation of rural areas, urban areas, and peri-urban areas. How do we go about it? You first divide the population into rural, urban, and peri-urban, and then draw a random sample across each strata, so that you will ensure that if there are minority subgroups, you are getting them adequately represented, or in fact even oversample the minority group as per the need of your study. So for example, here you look at this picture, the population is already separated into two strata based on some characteristic, and then you select randomly from each strata. Either you can do proportional to the numbers in each strata, or whatever sampling fraction you wish to choose. So finally, let's look at another elegant method of sampling that we often use in public health, and that is cluster sampling or area sampling. This is very useful when there is a natural grouping of units in the form of clusters. These clusters are mini populations and therefore are heterogeneous. So what we do is we take a random sample of these groups or clusters, and within each of the selected cluster, either we study all the units or draw a random sample of these units. And as you can see here, it provides logistical advantages. Let's assume you want to do a prevalence survey of tuberculosis in the whole of India. It's unimaginable to be able to draw a simple random sampling, because if we have to draw a simple random sampling, the first thing is we need to have a sampling frame, which is a list of all individuals in the population, and then draw randomly. And then if we get some people from one village down south, some people in the west, in the east, it is going to be logistically a nightmare to be able to conduct such a sampling. Whereas in a cluster sampling, you can list all the clusters and then draw a random sample of clusters. There are probably a few clusters that we need to visit, and in each cluster we study everyone, or maybe a random sample again within each cluster. So how does it work? So this is, if you look at this diagram, population in already in 5 clusters, let's say A, B, C, D, E, there are 5 clusters, and randomly we select 2 clusters out of 5, and then in each selected cluster we draw a random sample of units, and that's how our resulting sample will come about. The important thing is that we are not going to think about what are the problems of cluster sampling, but I have to caution you that the way we calculate sample size, the way we do analysis is going to be very, very different in cluster sampling as compared to simple random sampling, and that is something you have to keep in mind. Now, this is in brief the sampling methods that we have. Next, and the final part of this presentation, let us discuss about variables. What are variables? These are entities that vary in a study. These are the very thing that we are interested in. So, and whenever you hear the term variables, you might have heard of several jargon associated with them. Qualitative variables, quantitative variables, continuous variables versus discrete variables, nominal variables, ordinal variables, interval ratio variables, or dependent versus independent, exposure versus outcome. Sometimes can be highly confusing with all this jargon. I think now it is very clear with our previous presentation as to what is an exposure variable and what is an outcome variable, or what is a dependent and an independent variable. So I'm not going to discuss that here. Let's look at a classification, a framework as to how we can understand the different types of variables. Variables can be broadly divided into 2 major categories: qualitative, quantitative. Quantitative or numeric variables. Whenever a variable is expressed in terms of numbers, that is called as quantitative variables. Whereas when a variable is expressed in terms of a quality, then it is a qualitative variable or a categorical variable. Let's take some examples to understand this further. Quantitative variables are further divided into continuous variables and discrete variables, whereas qualitative variables can be further divided as nominal variables and ordinal variables. Let's go through in detail of each of them. What's a discrete variable? It's a quantitative variable, but which means that it is expressed in terms of numbers, but those consists of separate indivisible categories. For example, number of children in a family. It can take only whole numbers. It can be 0, 1, 2, 3, 4, so on. It can't be a 1.5. Doesn't make any sense. Number of students attending a class. Again, whole numbers. It is numbers, but only whole numbers. It contains separate indivisible categories. Number of medical visits to a clinic, for example. That's another example of a quantitative variable, but discrete. Whereas in a continuous variable, there are an infinite number of possible values that fall between any two observed values. Let's take an example. Height. You can have 155 centimeters, 155.5 centimeters. You can cut further and say the person's height is 155.45 centimeters, and it still makes sense. So the main characteristic of a continuous variable that you can divide it into infinite number of possible values, and each value will still make sense. So another example is weight or age or time. These are examples of, they are quantitative variables but continuous. What's a nominal variable? So this is a qualitative under qualitative variables. Nominal variable, nominal means names. So sex is a variable, male, female, 2 categories. It's a quality that it is expressing. Religion, Hindu, Muslim, Christian. This is another example of a nominal variable. Just categories. There is no order within those categories. There's nothing like one is bigger than the other or greater than the other. Colors, red, blue, green, yellow. Just discrete, qualitative categories. This is an example of a nominal. Or blood groups. There's another example. Please note that there is no order in these categories. And one of the special categories under nominal variable is if the data falls into 2 groups only. That means if it has only 2 categories, then it is called as a binary variable or a dichotomous variable. For example, there can be several situations when there is either you have the disease or you don't have the disease, or whether it's somebody is dead or alive, or some test result is either positive or negative. So when you have only 2 possible categories, then we call it as dichotomous variable or a binary variable. Now, what is an ordinal variable? It is similar to a qualitative variable, but there is an inherent order to these categories. For example, severity of pain. You can have no pain, minimal pain, moderate pain, and severe pain. You can have grades of malnutrition. Mild malnutrition, moderate, and severe malnutrition. Or another example I can think of is staging of HIV disease, for example. Stage 1, stage 2, stage 3, stage 4. There are categories, they are qualitative, but there is an order, inherent order to these categories. But there is no information about the size of the interval. We can't say that the difference between no pain and minimal pain is the same as between minimal and moderate pain. We can't be that detailed, but yes, it can still be placed in terms of some order. So this is how we divide. To summarize variables, there are 2 categories: qualitative variables, quantitative variables. Under quantitative variables, you have continuous and discrete. Under qualitative variables, you have nominal and ordinal variables. So this concludes our presentation, and I've given here some references for further reading. These are great textbooks on epidemiology where you can read and learn a lot more about the concepts that we have discussed, and they have been very helpful. And there is also a series of articles on epidemiology which was published in Lancet. They also act as a good reference for you to learn more on these concepts. Thank you very much.